On affine reachability problems. This is the title of my talk. My name is Stefan Jaax. I'm from Technische Universität München. This is joint work with Stefan Kiefer from the University of Oxford. Affine reachability is the following problem. You're given some numbers, x and y, those are integers, and you're given a finite set f of affine functions. Those are functions of the form x maps to alpha x plus beta, where alpha and beta are integer coefficients. And you're supposed to give the following Boolean output. Is y, your target value, reachable from x by applying mappings from your set of affine functions f? You are allowed to apply arbitrarily many functions in arbitrary order. So here's an example. Say your initial value is x equals 1, your target value is y equals 5, and your set of functions consists of three functions. f1 maps x to 2 times x minus 1, f2 maps x to minus x, and f3 maps x to 3 times x plus 2. Then the output should be yes, because you can reach y by first applying f2 to x, then f1, then again f2, and then finally f1, and you obtain your target value 5. So notice you can apply each function arbitrarily many times, and you're not required to use all functions in your set. What is the complexity of this problem? It is known to be in PSPACE, and it is NP hard. So it lies somewhere between NP and PSPACE. As of now, we do not know the precise bound, and establishing such a precise bound appears to be quite difficult. This is why, for the purpose of our paper, we focused on two related problems. First, we looked at affine reachability with states. Here, the functional application is restricted in the sense that what functions you're allowed to apply at each step is dependent on your current state. Second, we looked at related problems in upper triangular matrices. This is motivated by the usual correspondence between affine functions and upper triangular matrices of the form y equals alpha times x plus beta, precisely if the vector y with the homogeneous coordinate 1 equals the matrix alpha beta 0 1 multiplied with x with the homogeneous coordinate 1. So let's first start with affine reachability with states. So this is the following problem. You're given some transition graph that specifies at what state which function is allowed to be applied. So in the graph above here, you have three states S, Q, and R, and for instance, you're allowed to apply the function x maps to minus x at state S, and then you have to transition to state Q. And then the affine reachability with state becomes the following problem. Again, you're given some initial value x and some target value y, and additionally you're now given some initial state qx and some target state qy, and the question then becomes, is there a sequence of affine functions f1 up to fm such that you can reach y from x by applying the sequence to x, and furthermore, at each step the function application should be legal in the sense that you can go from your initial state qx to q1 via an arc labeled with f1, you can go from q1 to q2 via an arc labeled with f2, and so forth until you reach your target state qy for some intermediate states q1 up to qm minus 1. So this means the order of your function application is restricted by the state you're currently at. What is the complexity of affine reachability with states? This is our main theorem. Affine reachability with states is PSPACE complete. The PSPACE upper bound already follows from a result by Finkel, Göller and Hase from 2013. There they showed that the reachability problem is PSPACE complete, even in the case where you are allowed to have arbitrary polynomials, not just affine functions on the arcs. In a slightly orthogonal direction to our result, Niskanen showed in 2017 that polynomial reachability without states is PSPACE complete. That is to say, you only have one state. So how did we go about proving PSPACE hardness of affine reachability with states? We proved this via reduction from bounded one counter machine reachability. This is a modified version of affine reachability with states, and it is modified as follows. You're now additionally given some bound b, which is a positive integer, and this integer is encoded in binary. And furthermore, all your affine functions that you're allowed to apply are of the form x maps to x plus or minus some offset c, and this c must be in the interval between 0 and b. And finally, all intermediate values during your function application must be in the interval between 0 and b. So you're never allowed to go below 0 or above b. And as I just said, we reduce bounded one counter machine reachability to affine reachability with states. How does the reduction work? So say you want to simulate a step from your bounded one counter machine that goes from some state q to some state r and applies some offset plus or minus c. The bounded one counter machine would be blocking as soon as you're outside the admissible interval between 0 and your upper bound b. Of course, we do not have such a blocking behavior in affine reachability, so we have to come up with a construction that somehow keeps track of when we get into the inadmissible area and make sure that we stay then outside this area forever. And for this reason, we have some intermediate state r prime, so we first apply our offset. And after we applied the offset, we guess the current value of our counter, so to speak. So if we're in the admissible area, then we are between 0 and b, and then we make some guess that the value is either 0, 1, up to b. And each arc corresponds to one guess and to one function application, and then we just transition to r. The guesses will be made in such a way that if the guess is correct, and we get the correct counter value, then there should be no effect of the function application. So fi of I should equal I. And furthermore, if the guess is wrong, either because we are already outside the admissible interval, or because we simply guessed the wrong value between 0 and b, then we should be catapulted way outside the interval. This means we should be catapulted outside of the interval minus b and 2b, such that subsequent applications of offset plus or minus c will not bring us back into the admissible area. Now, if we set some constant k to the value 2 times our upper bound b plus 1, then it is not so hard to see that the functions fi defined in a way that x maps to k plus 1 times x minus k times I satisfy the above two requirements. So the first requirement, that fi of I equals I, is easy to check. K plus 1 times I minus k times I clearly equals I. The other requirement, that fi of x is not in minus b up to 2b for every x unequal to I, is also not so hard to check. This construction is not polynomial because, remember, our upper bound b is encoded in binary, and we would have 0, 1 up to b transitions, so this is clearly not polynomial. So we have to modify our approach a bit. Let me illustrate the idea for upper bound speed that equal 2 to the power n minus 1 for some n. This means that you can represent b by a sequence of binary digits where all the digits are set to 1. Then guessing some I between 0 and b amounts to guessing which of those binary digits should be flipped to 0. What we can then do is we can first apply the part of the function that is common to all I, namely k plus 1 times x. This is what we do here. We go from our state s to some intermediate state s0 by applying k plus 1 times x. And then what we do is we simultaneously guess the binary digits and apply the corresponding offset. So we start at the 0th bit, and if we guess it to be equal to 1, then we subtract chi times 2 to the power 0, otherwise we just apply the identity. And then in the 1th bit again, the above arc corresponds to the guess that the first bit equals 1, and the arc below corresponds to the guess that the bit equals 0, and so forth until we guessed all bits and applied all offsets. And it is not so hard to see that we can generalize this construction to arbitrary b. So this gives us PSPACE hardness of affine reachability with states. Now let's turn to reachability problems in upper triangular matrices. Remember, this is motivated by the isomorphism between affine functions and reachability in upper triangular matrix space. Here we consider the problem in slightly more generality, where we assume that we are given some finite set of generator matrices over the integers of dimension 2 by 2, and we look at the monoid generated by those matrices by arbitrary multiplication of those matrices. Notice that also the anti-product is allowed here. We define this to be the unit matrix, so the unit matrix is always part of the monoid. And then we can consider the following 3 natural reachability problems. The first one is membership. Here you are given some matrix A and your generators, and you are supposed to answer whether A belongs to the monoid. The second one is vector reachability. Again, you're given the generators and also some column vectors x and y, and now you're supposed to tell if y equals a times x for some a in your monoid. So this is basically the analog of affine reachability now in this matrix space. And the third problem is scalar reachability. In addition to your generators m, you're also given column vectors x and y and some scalar alpha, that is some integer, and you are supposed to tell if you can transform x into another vector via multiplying some element from your monoid, such that y transpose times this new vector equals some scalar alpha. So in a sense, you're asking, can I transform my x into a new vector that is in a certain direction and in a certain angle from my vector y? Since the 1970s, it is known that all 3 problems are undecidable for dimensions 3 by 3. But the case we are considering here is the case 2 by 2. And here decidability is still an open problem after 50 years. So tackling the general reachability problems for 2 times 2 matrices appears to be quite hard. Motivated by the correspondence between affine reachability and reachability in upper triangular matrices, we focused on upper triangular matrices instead. So we looked at membership, vector reachability, and scalar reachability. And even there, we only managed to establish lower and upper bound for certain special cases. We mainly looked at restrictions on the set of generators. If the generators for our monoid all have plus or minus on the diagonal, then we obtain NP completeness for all three reachability problems. We can further improve this to P time if we assume that there is exactly one on the diagonal and one minus 1 on the diagonal for each generator. Now I'm going to sketch the NP completeness proof for the case where the diagonal elements are plus or minus 1. So here the plan is to reduce membership to one-dimensional Z-VAS reachability. VAS stands for vector addition system with states. In our terminology, Z-VAS reachability is just affine reachability with states, where the affine functions are restricted to the form x maps to x plus or minus some offset c. And then there's the theorem from 2014 that states the following. Given the transition graph for your Z-VAS reachability problem, it is possible to construct some existential Pressburger formula phi of q, q prime, x and y in polynomial time such that you can go from your state q and your integer value x to some other state q prime and some integer value y if and only if the formula is satisfied for this assignment of q, q prime, x and y. Now if we somehow manage to polynomially reduce our membership problem to Z-VAS reachability, then we obtain the following corollary. Membership queries are definable in existential Pressburger and P time, and since existential Pressburger is NP, we obtain the NP upper bound for membership. Of course, from the formula for membership, we can derive equally succinct formulas for scalar reachability and for vector reachability, and so we also obtained an NP upper bound for those problems. So let me now sketch how the reduction from membership to Z-VAS reachability works. For the reduction, it helps to consider how a non-deterministic Turing machine might solve the membership problem. So assume the machine is given some matrix A and the set of generators M and supposed to answer whether A belongs to the monoid generated by M. And here we already assume that there's this restriction in place where all the generator matrices have plus or minus 1 in their diagonal components. What the Turing machine can do is it can store the currently reached matrix in some accumulator matrix, and we denote here the assignment at different time points by A1, A2, I3 and so forth, and initially the accumulator is set at time point 0 to the unit matrix, which we can always reach, and now to compute the next accumulator value at time point n plus 1, the Turing machine can do the following. It can non-deterministically pick some generator from the set of generator matrices, and then it can multiply this generator to the right to the old accumulator value to obtain the new accumulator matrix. And as soon as the current accumulator matrix equals the target matrix, the Turing machine returns success. This clearly works. Now the question is, can we represent this algorithm in a Z-VAS reachability problem? The diagonal elements of our accumulator only alternate between the values plus and minus 1, so we can clearly represent them in the state space of our transition graph. But then we would like to represent the upper right value of our accumulator, this value an plus 1, by the current number value in our reachability problem for Z-VAS reachability, And here we are faced with a problem, because when you look at how an plus 1 is computed, then you see that an plus 1 equals t times an plus sn plus a. So it's not of the Sivas form where you just add or subtract a constant offset, because you have the scaling by t here. So this poses a problem. Solve this issue by modifying our non-deterministic algorithm slightly. This algorithm works in a similar fashion, except that when we update the accumulator matrix, we update the diagonal elements as before, but we additionally multiply the lower right diagonal element on top of the rightmost component. And we return success whenever our accumulator matrix equals the target matrix, except that the upper right component equals the product of the lower diagonal element of the target matrix and the upper right element of our target matrix. You can show by a simple induction on n that this algorithm works, and it also helps us now to represent it in a Sivas, because when you look at the value of this upper right component here in our accumulator, tn plus 1 times an plus 1 equals tn times an plus tn plus 1 times sn times a. Forget about the right half here. What is important is that you have something of the form the new value equals the old value plus some constant offset. And this is exactly the shape we want to have. Now we can encode everything in a Sivas reachability problem. This finishes the proof for the NP upper bound. The NP lower bound can be proven by encoding a variant of subset sum into membership queries, and the reduction works similarly for vector reachability and scalar reachability. Then we looked at more special cases of membership in upper triangular matrices. The case where the generators have strictly non-zero elements on the diagonal is NP complete. The case where there's exactly 1 0 on the diagonal is PSPACE. And the case where there's no restriction on the upper triangular matrices is scalar reachability hard for upper triangular matrices. We also looked at special cases for vector reachability. The general case in upper triangular matrices is hard for affine reachability over the rationals, and the case where the lower right component is non-zero is in PSPACE. Then we looked at the special case of mortality. Mortality is the following variant of membership. You're supposed to say whether the zero matrix is part of your monoid. And we showed that mortality is NP complete in the case where the determinant of our generator matrices is strictly either 1 or 0. There is a previous result that showed that NP completeness holds for determinant plus or minus 1 or 0. So this is an improvement that we just require 1 and 0 here. By the way, mortality is known to be undecidable for 3x3 matrices. Decidability of mortality for 2x2 matrices is still unknown. Then we looked at some sign-invariant version of scalar reachability and showed that this version is polynomially reducible to membership. This is the following version. You given your upper triangular matrices as generators and column vectors x and y, and now you're supposed to say whether y transposed times m times x equals plus or minus 1 for some m in your monoid. To sum this up, we showed p-space completeness of affine reachability with states. The precise complexity of affine reachability without states is still an open question. We only know that it's somewhere between NP and p-space. And we gave various upper and lower bounds for special cases of membership, vector reachability, and scalar reachability in 2x2 integer matrices. The decidability of the general case is still open for 2x2 integer matrices. Thank you for your attention.